So this really tells us about the general structure of the liquid crystalline material. So the next level is that we design certain types of descriptors that we use for liquids and for crystalline materials. The question is, can we apply them to liquid crystalline materials, and whether they are really appropriate to describe them, right? So if you want to design an experimental setup, or if you want to describe the difference between different flavors of the liquid crystalline material, what do you do? What kind of technique do you use? So I can tell you that, for example, diffraction experiments can be used on the liquid crystalline materials, and they can tell you something about the internal structure. And just as a sanity check, I will ask you, if you do a diffraction pattern and you do an experiment on a plastic crystal versus liquid crystalline material, what kind of a diffraction pattern can you expect? So I'm drawing the intensity of a diffraction as a function of the scattering angle. And for example, if you focus on the plastic crystal, what would you expect to see in the diffraction pattern? Yes?
Because plastic crystals don't have orientation, so it's going to have a broader peak because the lens across all different surfaces.
Okay, so what you just mentioned is that because the molecules do not have the orientational order, you would expect broader peaks. But you're saying that you would expect peaks, right? Why would you expect peaks in the plastic crystal? That is the correct answer, just to tell you. So, yes?
With the plastic crystals, with plastic crystals, you still have planes.
That's right.
You can still have a interplane distance.
That's right. So if you remember, I will just draw just a very generic diffraction pattern from a plastic crystal. So if you remember that the diffraction and the existence of the peaks in the diffraction experiments was driven by the fact that you had a translational order, that you had very well-defined planes, and you could then calculate the scattering amplitude and the direction where the constructive interference will happen. So this is still preserved in plastic crystals, right? So you still have these molecules, but the broadening of the peaks will come from the fact that each molecule have a completely different orientation. So I can ask you a question, how would the diffraction pattern from a liquid crystalline material would look like? Would it be very similar or very different? Yes?
I'm not sure if we would have any peaks because there's no positional order, so there's no real,
Okay, so the question then, that's the correct answer. So the question is, diffraction pattern from a liquid crystalline material, let's say from a nematic liquid crystalline material, would be very, very similar to a diffraction from an amorphous material. And this is generally relatively broad peak, right? So you do have some kind of short-range order, which will give you the information, or it will position the peak. But in general terms, this would be very, very broad peak. There would be one peak, right, as for any amorphous materials. And this typically tells you about the distances between the first neighbors in the material, etc. Okay? So already from the diffraction pattern, you can distinguish between plastic, for example, and the liquid crystalline material. And if you, for example, had a smectic versus nematic liquid crystalline material, this would be more ordered. So you would start eventually to see some peaks, etc. But again, this already tells you that you can't really learn too much about the internal structure of the liquid crystalline material simply from a diffraction. So you have to think about different ways to describe that. Okay? So another descriptor that we talked about extensively was the pair distribution function. And this is just a summary of what we learned previously. So just to remind you, so that the pair distribution function was given by this equation. And the meaning of this function was simply, what is the probability that you will find an atom from an average atom within the material? So if you select one particular atom, the pair distribution function would tell you what is the probability that you will find another atom at a certain distance. And the pair distribution function had a general shape that looked like this. So if this was the pair distribution function as a function of R, in general terms, it would have a shape like this for, let's say, disordered materials. And this distance here, where this pair distribution function converges to a value of 1, was called a correlation distance. So we can use the same concept for liquid crystalline materials. So the pair distribution function was a very generic descriptor that we mentioned that can be used for any type of a material. So it is the general shape of this equation that will change and that will tell you something about whether the material is amorphous or the crystalline. So again, we can apply this and we can assume that, for example, these, instead of individual atoms in this picture, I have these very elongated molecules that form my liquid crystalline material. So the question is then, how would the pair distribution function, namely, how would this correlation distance look like if you have these liquid crystalline materials? So here you have to distinguish between intramolecular and intermolecular. So what that means is that, for example, if I take an atom within an individual molecule, there is high order within the molecule itself. So the pair distribution function within the molecule resembles something similar to a crystalline material, right? But if you look more broadly, if you go from that particular atom that I circled here, and if you look at, try to calculate what is the pair distribution function further away at larger distances, this will be described as intermolecular correlation distance. So let's assume that we talk about a nematic phase. So the nematic phase is shown here on the top. So again, orientational order, there is no positional order. If I ask you a question, what would be the correlation distance in this particular case if we focus on these intramolecular distances? So how far from a given atom can you predict the position of another neighboring atom if you're simply thinking about interatomic distance, intermolecular distances? Yes?
Only the length of one atom, or like the length of one molecule.
Exactly. So you would roughly be able to predict the position of other atoms within the length of this particular molecule. So this particular correlation distance would be on the order of L, where L is the length of that molecule. So then I can ask you a question, what is the intermolecular correlation distance? Okay, that was not the correct answer. Okay, so what would be the correlation distance for intermolecular distances? How far away from that particular atom would you be able to predict the position of other atoms when you go outside of that given molecule? Yes?
Maybe something like just like L, because you can't, because there's no order. You don't know how close they are.
Okay, so there is no order, but for example, if I ask you a question, what is the correlation distance in a liquid? The pair distribution function for gases is a line, right? But for liquids, if you go back, for liquids and amorphous materials, there are sort of wiggles, right? So this correlation distance is usually a couple of near neighbors distances. So the nearest neighbor distances in the liquid crystalline materials are simply the distances between different molecules. So in principle, then this correlation distance in the perpendicular and in the parallel direction relatively to the orientation of the molecules would be close to roughly 2 to 5 lengths and close to 2 to 5 diameters, where the diameter would be this dimension of the molecule. So what that simply means is that although there is no, this is a liquid phase in terms of the translational order, you can predict the position of individual molecules roughly at the order of 2 to 5 molecules. Okay, so just to demonstrate that, well, again, the pair distribution function can be used in these materials, but it can also distinguish between the nematic and the smectic phase. I can ask you the same question, right? So I can ask you a question, what is the correlation distance for intermolecular correlation in the smectic phase? And the answer would be similar to the nematic case, because we are simply looking at identical molecule, but these molecules are now in the layered structures. But the intermolecular correlation distance would be different. And which one would change? How far within the layer can I predict the position of the molecules? Maybe someone else. I will come back to you if there is nobody else. Okay, yes?
The same within the layer? Be like 2 to 5 diameter?
Yes. So within the layer itself would be exactly the same as in the case of the... So I can predict the position of the molecules within this one layer roughly as it was completely disordered material, right? And then in the direction of the stacking, that would be how much? Yes? A lot more. It would be much longer, yeah. So, okay. And I will just put the sign like this. It would be very. So I can then ask you a question finally. If I measure a pair distribution function, let's say of a nematic crystal, what would I see? There are different correlation distances. How would that function look like? Any guesses? So it would be a superposition of completely 3 different pair distribution functions, right? So you would plot one pair distribution function, this pair distribution function, and this one, and you would superimpose them, and it would be a very complex pair distribution function. And again, if you do measure the pair distribution function, there are methods how you can deconvolute that, so you get the relatively complex function, and there are methods how you can deconvolute them, and then calculate, for example, what is the order within the